Alright, let's do some example problems with adiabatic processes, and then we'll touch on, let's do one with adiabatic processes, and then we're going to do some thermal statistics as well. Alright, air at a gauge pressure of 0.3 atmospheres and a temperature of 25 degrees C escapes from an air tank, expanding adiabatically to a pressure of 1 atmosphere. What is the temperature of the air after expanding? Assume that the air behaves like an ideal atomic gas. Okay, so this is adiabatic expansion, right? And we've got our equation, PV to the gamma is a constant. What does that mean? What that means is if I measure at some initial point P times V at some initial point, and I do it at some final point, P times V to the gamma will be the same at the initial and the final. All right, are we given an initial pressure? Yes, we are given an initial pressure. It is 0.3 atmospheres, but that's a gauge pressure, so the absolute pressure is going to 1.3 atmospheres. Do we know what the final pressure is? Yes, the final pressure is going to be 1 atmosphere. Now, these are not SI units, but notice when we solve this equation, we're not going to solve this one, we're going to solve one like it. The pressures will end up being a ratio. So as long as they're absolute and not gauge pressures, the units will cancel out. All right. We are not given an initial and a final volume, however, so this equation's no good. It also doesn't have the thing that we want in it. So we go back to our textbook and we say, oh, where was that? There's an equation for, like, with temperature and, wait, there's one for temperature and volume. There's not one for pressure and temperature. That's really lame. What am I supposed to do? Well, the answer is, this is the only equation you need to remember. All right? You can get the other variants of this from the ideal gas law. So let's start with this. Let's start with this version right here. It's clearer, but this has pressure in it, which we know, but it also has volume, which is we don't know, and we want temperature. So how can I get rid of volume and replace it with temperature? Well, if I look at the ideal gas law, PV equals nRT. All right. Pressure initial V initial equals nRT initial. Pressure final, V final, is equal to nRT final, right? Okay, so V initial is just going to be nRT initial over P initial. And V final is just going to be nRT final over P final. So we can plug this into our equation. So P initial, V initial is just nRT initial over P initial. To the gamma is going to equal P final. V final is just nRT final over P final to the gamma. All right, now we have an N and an R to the gamma on both sides. And so we can cancel those out. And then this just becomes, I've got pressure to the first power divided by pressure to the gamma power. So this is just going to be pressure initial to the 1 minus gamma. Then we've got initial temperature to the gamma, so T initial to the gamma is equal to the same thing with the final pressure and temperature. So it's pressure to the 1 minus gamma, temperature to the gamma. So the equation we came up with was pressure to the 1 minus gamma times temperature to the gamma is equal to pressure final to the 1 minus gamma, temperature final to the gamma. All right? So we're given the initial, we have the initial and final pressure. We are given the initial temperature, we want to find the final temperature, so temperature final to the gamma, we solve for that, and we just get temperature initial to the gamma times pressure initial over pressure final to the 1 minus gamma. Once again, look, we have ratios, all right? So it doesn't matter whether we do this in atmospheres or PSI or pascals, because the units will cancel out. As long as they are absolute units. Gauge is not an absolute unit, so we can't use it, all right? Temperature, same thing. We're going to put in a temperature, we're going to get a temperature. So it doesn't matter what unit we use for the temperatures, but it must be an absolute temperature scale, which means it can't be Celsius, can't be Fahrenheit. It's got to be Kelvin, all right? Because that's the only absolute one that we know. All right, if I take the gammath root, right, taking the gammath root is like raising both sides to the power of 1 over gamma. This becomes temperature final equals temperature initial times pressure initial over pressure final to the 1 minus gamma over gamma power. All right, plug in your numbers and you get your answer. All right, now let's do a thermal statistics problem. About how many molecules of air in this room have a velocity of 200 meters per second? All right, I'm not giving you a lot of information. You're going to have to make an estimate. You're going to throw in some things and make some guesses. And when you do that, you come up with a very exact answer, and that is 0. How many molecules of air in this room have a velocity of 200 meters per second? None. If you find one, I'll say go measure it more carefully, and you'll say, oh, it's really 200.000001732. All right, so the point is, when we do statistics, we're never looking for an exact answer. So let's ask a better question. About how many molecules of air in this room have a velocity between 200 and 201 meters per second? All right, so how do we find that? All right, the book gives you this equation. N sub v is equal to 4 pi n times m naught over 2 pi k Boltzmann t to the 3/2 times v squared e to the minus m naught v squared over 2 k Boltzmann temperature. All right, so this is the number of molecules in our gas. This is the mass of the molecules in our gas. This is Boltzmann's constant. This is the temperature in Kelvin. This is the velocity. All right, so we know what all the things in this equation are, but what does this actually mean? What does this equation actually mean? Obviously, I can't plug in numbers and get the number of molecules, because I just told you the number of molecules at any given velocity is 0. So really what this equation is the thing that I integrate to find the number of molecules between one velocity and another velocity. So in other words, if I want to find the number between 200 and 201 meters per second, I'm going to integrate this, right? Integral NV dV from a velocity of 200 meters per second to a velocity of 201 meters per second. All right, so I just take this thing, stuff it in an integral, and do the integral, and that is how I would find the number of molecules. All right, now this is not an integral problem that's easy for you to do. So if I give you a problem like this, and I did give you a problem like this, you will use something like Mathematica to solve it. All right, but just so that we know how to solve it, what do we plug in for everything? I know what 4 is, I know what pi is. What is n? How do I find the number of molecules in this room? Well, I'm going to use the ideal gas law. PV is equal to, let's use the number of molecules version, number of molecules K Boltzmann T. All right, so I solve this, and it's just going to be PV over K Boltzmann times T. All right, I know K Boltzmann. What's the temperature in the room? Probably around 300 Kelvin. What's the pressure in the room? Atmospheric pressure. Then I just need to know the volume of the room. So look around at your room, you know, how tall are the ceilings? You know, maybe 10 feet. You know, how wide is the room? Maybe 15 feet, maybe 12 feet, you know, across. All right, so I can calculate the volume. So, right, by estimating some things, I'll leave it up to you to see if you really want to know the answer. I'll let you plug things in. But I have a way to get a value for n for my room. What is m sub naught? That's the mass of my molecules. All right, so most of the air in the room, the largest fraction is nitrogen, and there's some oxygen and some other stuff. So maybe just to make an estimate, we'll look up the mass of a nitrogen molecule, 2 nitrogen atoms. All right, find that in SI units, and then we plug it in. All right, and then we have everything we need. We can plug it into this equation. We can do the integral, or probably, yeah. Then we get our answer. All right, so I'm not going to go through all the details. I just wanted to point out how we would do this. So the number of molecules is just the integral of this thing dV from our initial velocity to our final velocity. And I'll let you work out the details, all the fun stuff.